In a simple model, the value v of a car depends on its age t in years, and some information is given. Value when new is 20,000, so that's going to be when t is 0, and value after 1 year, t is 1, is 16,000. Use an exponential model to form the car A, a possible equation linking b with t. Well, a general equation we can write down for an exponential model is v equals a. I mean, I quite often use capital A, but I'm going to avoid it because we're using car A. So a e to the kt. You don't have to go with that, and I'll talk about an alternative in a minute, but this is a good one to remember, and it's also in a nice form to differentiate if you were asked about the rate of change. So it's to be honest, you're just going to remember one. Let's go with this one. So when t is 0, we're going to get 20,000 equals a e to the 0, but that's just 1. So actually a is 20,000. And then when t is 1, got 16,000 is equal to 20,000, my new value for a, times e to the k. By the way, I'm expecting k to be negative here because it's decreasing in value. You could even put a minus into the equation here if you wanted to. I didn't really feel like it was beneficial in this situation, but there's differential equations where it really becomes useful to know that. But I'm going to leave it as positive, well, just a k here, but I'm looking for it to be negative afterwards. So then e to the k will be 16,000 divided by 20,000. That just becomes 16 over 20, or actually 4 over 5. So k is ln 4 over 5. That's the exact value. But I'm going to write my answer to 3 significant figures. So ln, remember it's a model, so leaving answers exact is not particularly useful. Minus 0.22314. So finally, v is going to equal 20,000 e to the minus 0.223, I round it to 3 significant figures here, times t. Just for info, an alternative would be to go for v equals a. I'll stick with a as my kind of constant there. And then I'll times by b to the t. So rather than using e as my base, I'm using, like, which is a number I know, I'm using a number that I don't know. So I've still got two unknowns. I'm actually still going to get a is 20,000 when I substitute t equals 0 in, but it's like a different exponential now. If you substitute 16,000 in, we just get b here. So there's no k or anything. And then b is actually going to be 16 over 20 or 4 over 5. You get quite a neat answer. It's going to be 20,000 times 0.8 to the t. So you might prefer to do that. I actually think it looks a bit neater here. It tells you that every time time goes up by a year, it's going to decrease by 20%. You just get that naturally. You could go from the exponential to this, by the way, because you could actually work out what e to the minus 0.223 and so on is, and then raise it to the power t. It would actually be 0.8. So, you can go between the two. It's just if you're starting it out, like these are the two different routes. It's going to be hard to differentiate. You're going to have to get it in terms of e to the kt. So look, they both have their uses. I would say if you're just going to learn one method, then it's this one because you're just ready to differentiate and find the rate if you need to, rather than having to mess about with it. But both are fine, and I ideally like obtain an understanding of each of them. The value of car A is monitored over a 10-year period. Its value after 10 years is 2000. Evaluate the reliability of the model in light of this information. So, so when t is 10, the model predicts b equals, and I'm just going to substitute 10 into that equation. I'm going to use this exact answer for k as well, actually. So 20,000 times e to the k times 10, 2147.4. And, it's a little bit out. It's, a bit under 10%, a bit more than 5%, but it's pretty close. This is about 2000. It's, when you do it on a model, you can't expect it to be perfect. There's going to be some flaws. We're expecting this 20% decrease every year. So I think we can say the model is reliable over the 10-year period, that is. Whether it will continue to be reliable, we can't say for sure, but we had the starting amount. We've got the 10 years later, it's pretty close. Originally, I said it's correct to one significant figure. I don't feel that really is justifying it well enough, but yeah, you could add something like that. We then got another car, B, and we're told it has the same value when new as car A, so that's 20,000, but the value is depreciating more slowly. So just a little sketch actually of what is going on here. Actually, let me do it in. Okay, so the car A is looking a bit like this, and we want to come up with an equation for this new model. That's an exponential decay, by the way. Same starting value, but it's going down more slowly. Okay, so what we actually need is the same value of A. So A equals 20,000 as before, but we need the decay to be slower. And that actually means we need k to be closer to 0. I want to say like larger, but it's going to get smaller in kind of magnitude, but larger in that it's going to be less negative. That's probably the thing to say. So make k less negative. We still want it to be negative for it to be decaying. So e.g. K equals minus 0.2. Okay. And then it will follow this sort of pattern. Um, there's other answers, and I'd say have a look for the mark scheme if you're interested in that. I think this is like the kind of the textbook answer that's been asked for, and makes you don't have to make it like you don't have to change the model that much. Just keep the 20,000 the same, but increase k slightly, make it less negative, closer to 0. That will cause it to decay at a slower rate.